Welcome to the first video tutorial in a series for organic functional groups. This tutorial will introduce them in a broad sense, and then the subsequent tutorials will go into different aspects. Let's go ahead and get started. Alright, so functional groups are certain combinations of heteroatoms and bonds that are seen frequently coming off of our hydrocarbon backbones. So what do I mean by heteroatoms? Oxygen, nitrogen, phosphorus, sulfur, basically anything that's not carbon or hydrogen, right, is a heteroatom. And these are very important because the functional groups are what create biological activity. So they're the foundation of understanding biochemistry. So we have to be able to recognize these functional groups and learn their personalities. What do they do inside of us? Alrighty. Now R groups, those are the hydrocarbon backbone. You could think of it as the rest of the molecule. So it's important to understand the hydrocarbon backbone, and so, but then the functional group is what really gives it its personality, right? So you can think of the R group as the rest of the molecule, the hydrocarbon backbone. So here's an example. Sometimes students struggle a bit with R groups, so let's look at this example here. Here we have two hydroxy groups. We would call these alcohols. We would symbolically represent it as ROH. What happens is the hydrocarbon backbone becomes the R, and then we have the OH. Now here is a very different looking molecule, but as chemists we really see them both as alcohols. And so we would describe this as ROH. If we were talking about these two compounds at the same time, we may put a prime here to show that the hydrocarbon backbone of the molecule on the left is different from the hydrocarbon backbone for the molecule on the right. But both compounds would have very similar chemical reactivity, even though the hydrocarbon backbones, the R groups, are different. Alrighty, so let's get started on our functional groups. Now, the first group that we're going to look at will be the alcohols and the ethers. And we look at these together because they both have a carbon-oxygen single bond. So for alcohols, we've already seen we have the OH group. We follow our bonding patterns. This is how we expect to see oxygen, 2 bonds and 2 lone pairs. However, this hydrogen could be replaced with another hydrocarbon tail or chain. So notice the similarity here, that when we look here, they look the same. Alcohols with hydrogen, ethers with another carbon. So let's connect this with what we've learned in our previous chapters, right? So if we look at those oxygens, right, their electron geometry is tetrahedral, because there are 4 regions of electrons. However, the molecular geometry, when we're just looking at the atoms, we would describe them as bent. And now we can look at so that's the physical structure. Now let's look at the polarity and the electrostatics, looking at our intermolecular forces. When we look at the hydroxy group, the alcohol group, we recognize a very polar bond with the OH, and then we would see slight polarity with the ether, a small partial minus on the oxygen, tugging ever so gently on those carbons. So we can recognize here with alcohols that they are H bonders. However, with ethers, we have an oxygen, but it's not bonded to hydrogen. So with ethers, dipole-dipole would be the dominant intermolecular force. So we'll just say C above. Okay, so now that we've looked at alcohols and ethers, we will look a little more closely at alcohols on the next page. And get this centered. Okay, with alcohols, it can be important to classify them. So the way that we classify alcohols, though, is based off our understanding of bonding patterns. We know that with every alcohol, oxygen can only have 2 bonds, and one of those bonds has to be to hydrogen to be an alcohol, so then the other bond has to be to carbon. So if we look at these alcohols, they all share this same structural feature. But these alcohols will have different chemistry. That's why we need to classify them. So the classification comes from the number of carbon atoms bonded to the carbon bearing the OH group. So if we look here, we see that this carbon is only bonded to one other carbon. We would describe this as a primary alcohol. And so now let's compare this to the next compound. Notice this now, the carbon bearing the alcohol is bonded to 2 other carbons, right? Because carbon can have up to 4 bonds. So we would describe this as a secondary alcohol. And then in our third example, we see that the carbon that's bearing the alcohol is bonded to 3 different carbons. So we would describe this as a tertiary alcohol. So I've written it with symbols. Let's write primary, secondary, and tertiary. Oops. There we go. All right. Okay, so we have it in terms of symbols and English words. All right. Okay, so then let's practice this. So here's a molecule of cholesterol. So notice that the OL, all, lets us know that there's an alcohol. So I've asked you to go ahead and circle the alcohol group, but then go ahead and classify it. Is the alcohol of cholesterol primary, secondary, or tertiary? So there's the alcohol group right there circled, and we notice that we could think there's carbons here and carbons here. So it turns out that cholesterol is a secondary alcohol. All right. Okay. So a couple other things to note here are if an alcohol group is bonded directly to an aromatic ring, then we don't call it an alcohol anymore, we call it a phenol. So if we have our aromatic ring and we put the OH, right, then we would describe this as phenol. Now if you're wondering what that circle in the middle means, right, remember that aromatic rings have alternating double bonds and there is resonance there. It really creates a force field of electrons above and below the plane. And so instead of writing both versions, we simply write a circle in the center, right? And then if we wanted to make these into phenols, we would just add the OH on the side. All right. And phenols are very important biological molecules. And just for an example, here's serotonin, a neurotransmitter that includes a phenol. Alrighty, so to finish up on our ether and alcohols, we'll look for a moment at ethers. And here now we can see that we have the 2 R groups coming off of the oxygen. So symbolically, this would be R, and then we'd have the oxygen in the middle, and then we would have the other R group. So sometimes ethers, we would describe this as being symmetrical, because the 2 R groups are the same. But that doesn't have to happen. Notice here we have the first R group on the left is different from the R group on the right. So we'll use the prime, and so we would describe this as asymmetrical. Oops. Okay, so ethers show up occasionally in biological molecules, but they're not the most important. We'll see a lot more with alcohols. Alrighty, now we're going to move on to the functional groups that have carbon-oxygen double bonds. So let's get that centered. Alrighty, so the carbon-oxygen double bond is referred to as a carbonyl. And there are a very wide range of compounds that include the carbonyl. So when we see the carbonyl, we can't jump to any conclusions because what's going on, right? So this carbon to double bonded oxygen is the carbonyl group, and it's important to recognize it. But there's very different chemistries depending on what goes into position Z here. So Z, it can be as simple as a hydrogen or another R group or a hydroxyl group or another ether group, a carboxyl group. We could even put sulfurs in here, thiols, or we could put amines, right? And you all know that those hydrogens can be replaced with R groups. So once we recognize that we have a carbonyl, it's very important to look around and see what's going on with the substitution of this position. All right? For the carbonyl carbon atom, of course, we can put some lone pairs here on the oxygen to fill it in. The electron geometry around the carbonyl carbon, right, is that trigonal planar electron geometry, and then the molecular geometry is also trigonal planar because notice that there are no lone pairs around the carbon. Okay. And so now these carbonyl compounds are very important to our biochemistry, and so you want to be able to recognize them in a variety of forms, right? So when the Z group is a hydrogen, we would look at this, right? So here is our functional group. So we're always going to have the carbon backbone, and so for the aldehyde, we represent that in a condensed formula as CHO, the CHO, which is what, all right? And so this is the aldehyde. And aldehydes we will see primarily when we study carbohydrate chemistry. Okay, now here we have the carbonyl sandwiched between two R groups. So of course the R groups may or may not match. And then when we see a condensed formula with a CO in the middle, that is our flag that we have a carbonyl group. And in this case, when the carbonyl group is sandwiched between two hydrocarbon skeletons, we call it a ketone. Alrighty, now we're going to replace Z with the hydroxyl group. And so this results in, there's our carbon backbone. And then we can write this as CO2H. There's many varieties. The O's could be separated. And we recognize this as a carboxylic acid. Okay. Now, here again, here's our C double bond O. In this case, the hydrogen has been replaced with an R group. So we will sandwich that in the middle. So now between the two hydrocarbon chains, we will have the carbon with the two oxygens. And we will describe this as an ester. Sometimes, if you want to be really detailed, we would say that this is a carboxylic ester. So especially when we get into biochemistry, there's also thioesters and phosphate esters, which are described in a separate video tutorial. So there are several flavors of esters. Here's the first example. If we can replace sulfur with oxygen, so we would have our R group, and now we would have COSH, right? So that would be an example of a thioester. So recognize that whenever you see the word thio, it's telling us that sulfur is present. Alrighty, now when we get to the amides, our textbook is very thorough here, right? So here's our R groups. We'll keep those all the same. And then, right, so every amide is going to have CON. So the difference comes that we recognize that nitrogen is able to have up to 3 bonds and still be neutral. So if those are simply hydrogens, or we could have a hydrogen with an alkyl substitution, or we could have 2 alkyl substitutions. And technically, they could have different lengths of carbon chains, so it would look like that. And collectively, though, we describe all of these as amides. Alrighty, so it's really important to be able to distinguish between all of the different carbonyl compounds. And here's a good introduction for you. Now we'll look at amines, the last major functional group that we're going to study this semester. There we go. All right, so the amines do have carbon and nitrogen, but there's no carbonyl group. So we'll have some sort of carbon, and then there's our nitrogen, and nitrogen always wants its 3 bonds and 1 lone pair. So of course we could take, and these other hydrogens can be replaced with R groups. And so I'll finish showing you all of the examples. And then we'll just use the primes to show that the carbon chains can be different. All right, so let's briefly review our electron and molecular geometry. Nitrogen has 4 regions of electrons, so we describe that as tetrahedral. But however, one of the regions is a lone pair, so I've drawn this using the wedges and dashes to convey the molecular geometry. The atoms are going to form the shape of a trigonal pyramidal geometry. Okay. Now, because the nitrogen has the ability to bond to 1, 2, or 3 different carbons, we want to classify amines so that we can distinguish between them. So this classification is different from alcohols because nitrogen and oxygen have different bonding patterns. So here we can see in this first example with 1 R group, we would describe this as a primary amine. If we put 2 R groups onto the nitrogen, then it's a secondary amine. And you can see where this is going. If we have 3 R groups, it's a tertiary amine. And then the lone pair on the nitrogen is able to react. We will see that in future tutorials. It can react as a base, going out, and those negatively charged electrons can go out and create a bond to carbon. And so it is possible to have 4 bonds to nitrogen. Notice it's going to no longer be neutral. Here we have followed our neutral bonding patterns. Here we have disrupted our neutral bonding pattern. So notice that there is a formal charge. And so we would describe this as a quaternary amine. Right, so quaternary amine for 4. We don't have that for alcohols. Alrighty. So now let's compare and contrast. I have drawn for you 3 different compounds. So we have 2 amines and an alcohol. So let's go ahead and take a minute for you to classify these compounds and see how you're doing. All right, so this first example, 1 R group to the nitrogen, primary amine. And even though these R groups look very different, this is still another example of a primary amine. But remember that when we're looking at alcohols, we look at the carbon that bears the alcohol group. So even though this amine and this alcohol have the same hydrocarbon backbone, this is described as a primary amine, and this would be described as a tertiary alcohol. So it's important to keep in mind the differences in classifying amines and alcohols. And then to wrap up this tutorial, here is amoxicillin. So let's go ahead and circle and classify all the functional groups. If we do have an amine or an alcohol, go ahead and practice your primary, secondary, tertiary skills. Alrighty, so right here we see we have a phenol, an alcohol group on an aromatic ring. And then here's a carbonyl, right? So whenever we have a carbonyl, we have to look around. We notice that this carbonyl is part of an amide group. Write that neatly. And then we found another carbonyl, and we look around and we notice this is also another amide. And we have a third carbonyl, and when we look at this one, we see the hydroxyl group. So this would be a carboxylic acid. Okay, what's left? Let's see here. Oh, here is an amine, nitrogen all by itself. So this would be an amine. And when we look, it's only bonded to one other carbon, so this would be a primary amine. And we really, if you're wondering about this sulfur, we haven't talked about that. You don't really have to, you're not responsible for that in class. But if you're curious, we would describe it as a sulfide. Okay? So that would be optional. Alrighty. So this concludes the introduction to organic functional groups. Take some time now to work a few homework problems to reinforce your understanding.